I'm just going to go over the agenda real quick here. We're going to go over the basics, and I know this might be old hat to some of you, but if not, to some folks, if not, you'll learn something new. If it is old hat, maybe you'll learn something new anyway. So we're going to go over datums, geographic coordinate systems, map projections, and we're going to take a look at a few best practices in geographics when you're setting up your projects. I'll go ahead and wrap it up at the end. Now, I did use some references from the Association of Petroleum Surveying and Geomatics, the USGS, and NOAA, wonderful organizations for the GIS professional. Okay, let's get started. Cartography can be very confusing. There's a lot of strange terminology, a lot of complex mathematics, and as well as competing standards. So there's PRJ files, there's well-known text files, there's EPSG codes. It's not easy, and you know, people want it to be easy, and I certainly understand that. You know, with the advent of Google Maps, mapping GIS is pretty much accessible to everybody. But even saying that, we do need to learn a little bit about the basics. What's a datum? What's a projection? How cartography works? Because errors can be costly in the oil and gas industry, as you all know. You know, just a couple hundred feet on a bottom hole location could get you sort of in hot water, get you fined, or, you know, basically you're drilling a well for somebody else. So let's start with geographic coordinate systems. The thing to remember with a geographic coordinate system is we're always talking about a latitude and a longitude. A grid coordinate system, no, but a geographic coordinate system, it's always latitude and longitude based. Obviously 0 degrees at the equator to 90 at the poles, and the prime meridian is 0 degrees longitude. That is the meridian going from the poles through Greenwich, England. Minus 180 west and 0 to 180 east longitude. If it only could be that easy, but really the Earth is not a sphere. The Earth is actually an oblate spheroid, and when we talk about the surface of the Earth, we're really talking about which surface of the Earth. There is a lot of different mathematical representations of the surface of the Earth. These have been developed over centuries. So, and they're all called datums. Every mathematical representation of the surface of the Earth is a datum. And that datum is a mathematical best fit to the Earth's surface. In order to create a datum, you do need to know the distance between the center of the Earth, the exact center, and the equator, and the center of the Earth and the poles. And you'll see here that if you take a look at the little ellipsoid graphic here, there is a B and there is an A, that distance. That is necessary to define a datum. You have to know that because it allows you to come up with a best fit for the Earth's surface. Now, when I started in cartography and GIS many, many years ago, you know, I sort of got that, but I never really understood why there were so many datums. There's over 200 datums, and that's a lot, right? And there's a couple reasons for this. One, cartography is a very old science, probably 500 or 600 years old, and even when Columbus was sailing the ocean blue, the average Joe may have thought that the Earth was flat, but the reality was cartographers were already, even at that time, figuring out mathematical best fits for the round Earth. So over the centuries, obviously the accuracy has improved over and over and over again, so we have a number of different datums. The other reason why we have more than one datum is because the Earth has topography. So we got mountains, valleys, coastlines, and some datums, some mathematical best fits, fit better at higher elevations than they do at sea level. So that's the other reason why we have a lot of datums. Now, recently, the datums have become much more accurate. A very accurate datum, whole Earth datum, is WGS 84. That's the World Geodetic System datum, and that's a whole Earth datum. Datums generally are only useful over a portion of the surface of the Earth. For instance, the North American datum of 1927 is really only valid over North America. With the advent of geospatial satellite imagery and geostationary satellites, we've been able to measure the surface of the Earth much more accurately, and so create better datums. WGS 84 and NAD 83 are very accurate datums, although in the industry, at least in North America, because of all the historical spatial data, NAD 27, or the North American datum of 1927, is still often used. Now, the one thing you got to remember about this, and this is sort of the important thing, is that the latitude and longitude of any point on the Earth will vary depending on the geographic datum that is used to represent the Earth's surface. So I'm sitting here in Denver, and I'm at 40 degrees north latitude, minus 105 west longitude, in, let's say, NAD 27. Now, if I'm using the NAD 83 datum, the North American datum of 1983, that is not my lat long. It's different, a little bit. It's shifted a little bit. So that's where we get into trouble a little. We definitely get into trouble because if you do not know both the datum and the map projection, you will, and you import data, you don't know the source datum and map projection, and you try to import that spatial data into any GIS system, whether it be ours or ArcMap or whatever, and you will run into errors because things might be a little shifted. Now, you know, with satellite imagery, that's actually good because you can see it very quickly. If you don't have satellite imagery available, sometimes you don't see it, and then you run into problems. But this is really important, so just try to remember this always. It's the one thing that sort of got me a little confused when I started this. It never really dawned on me that my lat long depends on the datum that I'm using, the datum that I'm in. So how much could the error be? Well, here's the datum shift in meters between the North American datum of 1927, that representation of the spherical Earth, the spheroidal Earth, and the North American datum of 1983. And you can see here that you can be off around the coast, the west coast, about 90 meters. So, you know, lat long, if you have a lat long in NAD 27, and then you basically set up your GeoGraphix project in NAD 83, and using that as the datum, your well spot's going to be off by about 300 feet. So quite a bit. Now, it does get a little better as you move towards the center of the continent. And then it gets a little worse as you move towards the East Coast. But there's always going to be a datum shift. And generally, the datum shift is, well, almost always more than enough to cause problems. Okay, so we went over datums. Datums and geographic coordinate systems are often used interchangeably. And, you know, definitely, always when you hear a geographic coordinate system, you want to think lat long. Now we need to talk a little bit about projections here. Obviously, our maps, you know, we don't put a map on the surface of the Earth. It's a flat Cartesian map. And in order to create a map, we need to project points on the round Earth onto a flat surface. And there's a lot of different ways to do this that people have, well, scientists and cartographers have come up with over the centuries. You can see here that there's the cylindrical projection, where every point is being projected onto the surface of the cylinder. There's a conic projection, where obviously points are being projected onto the surface of a cone. You can project the points on the Earth's surface onto a plane. And of course, there's this thing called the transverse cylindrical projection, which is used in UTM zones. So we need to project locations on the roundish Earth onto a flat surface to make a map. Map projections help cartographers do this. And there are a couple of projections here that are really commonly used in North America. One is the universal transverse Mercator projection, where the Earth's surface is actually projected onto 70 different cylinders or zones. So those are the UTM zones. And many of our state plane zones use a UTM projection. Those states that are longer north-south than east-west tend to use the UTM projection. We use the Lambert conformal conic projection in North America quite a bit. Again, state plane zones use the Lambert conformal conic projection when the width of the state is greater from east to west than it is to north or south, like in Kansas, for instance. Now, map projections, whenever you project onto a flat surface, you're always going to get some distortion. The distortion will be in area, shape, distance, or angle. All maps have some distortion. What projection you use is going to determine what gets distorted. So, for instance, a lot of us use the universal transverse Mercator zones to set up our map display systems in GeoGraphix. What is not distorted in the universal transverse Mercator, universal transverse Mercator zone, is the angle. So UTM was developed by the United States military because they needed to figure out a way for ordnance testing to basically use the Pythagorean theorem to calculate distance. And obviously, if you were distorting your angle, you couldn't do that. And so the UTM system was born. There's a lot of projections out there. These are just the two most commonly used that we use in the petroleum industry, but there are hundreds. Well, maybe not hundreds, dozens and dozens of them. So different types of projections, we went over that. Maps always suffer from distortion. Always sort of remember that. A conformal projection primarily preserves shape, an equidistant projection primarily preserves distance, and an equal area projection primarily preserves area. Conformal projections like the conic projection preserve shape, for instance. Now, if you're only projecting a very small portion of the Earth's surface onto the, a cone or a cylinder or a plane, the distortion isn't too bad. The greater the Earth's surface that you're projecting, the distortion begins to increase and increase. That's why that in many maps, Greenland looks like it's almost the size of North America, and Greenland really isn't even the size of Texas. So about the size of Texas, I guess. So you can see that even though we can create a map, flat Cartesian map, there always is going to be some distortion, especially near the poles, for instance, if you're using a cylindrical projection. Okay, so worldwide UTM zones. Like I said before, there are 60 UTM zones that we can use. In North America, UTM zones generally go from about 10 to on the west side of the continent to about 19 on the east side of the continent. Those are the UTM zones we mostly are concerned with. State plane coordinates are also commonly used to make maps. State plane coordinates are the projection of latitudes and longitudes from the GRS 80 ellipsoid. Remember, that's a ellipsoid, a datum, to a flat mapping surface that is usually defined by state law. Now, these are the state plane zones. And you'll notice here that in Colorado, where I am, that would be the 501 state plane zone. that would be, that particular state plane zone uses a Lambert conformal projection, as some other ones do. Now, over here in Wyoming, you would use the UTM. Now, this is all sort of set up for you when you select your coordinate system, your map coordinate system in Geographics, but it's always good to sort of know. Okay, so we went over datums and projections, but what really is a coordinate system? It's actually a datum, a projection, a meridian, a unit of measure, both angular and distance. So in order to have a coordinate system, you have to have some way to define all of this information. And it's usually defined in a well-known text string or a PRJ file. PRJ files are commonly located in shapefile directories, and they contain the coordinate reference system information. A well-known text file is just a different representation of that, but it's pretty much completely the same, right? Same information, and I'll go over that in a second. Now, EPSG codes are a numeric shorthand for coordinate reference systems. So let's say you have a coordinate system, Colorado State Plane North, US survey feet. There is a specific EPSG code for that. EPSG stands for European Petroleum Survey Group, a now defunct group, but the EPSG codes have lived on, and they're actually becoming more and more used in GIS software, to the point where, people think about a coordinate system as an EPSG code, not even as a PRJ file or a well-known text string. But this is the kind of information that is in one of these PRJ files or well-known text files. Now, generally we just sort of gloss over this, right? Okay, do you have a PRJ file for the shapefile? Yeah, okay, great. I can get it into GeoGraphix, or I can get it into ArcMap. But it's instructive to actually look at the type of information that is in one of these files, because this information defines the coordinate system. It's the definition of the coordinate system. So here we have a NAT 83. That's the projected coordinate system, NAT 83, Colorado North, feet US. So it's US survey feet. There's a geographic coordinate system. That's NAT 83. That is the datum. It's the North American datum of 1983. We have a spheroid defined. That is the ellipsoid. And those two numbers are the A and the B distances between the center of the Earth and the equator, and the center of the Earth and the pole. Notice that we have an EPSG code for every one of these. This particular coordinate system uses the Greenwich meridian as the 0 longitude. We use degrees, right, for angular measurement, and US survey feet for distance measurement. Now, because this particular state plane zone is longer east to west than north or south, we're going to use the Lambert conformal conic projection to project points on the surface of the Earth onto a flat surface. Then there's a lot of other things here, the parameters. Some of these you may be interested in, some of you may not, but the ones that you should sort of look at are central meridian, which is the center of each state plane zone. There is a meridian, and actually there's least distortion at the meridian. And then there's a false easting and a false northing. In order not to have negative numbers for our Cartesian grid coordinates, there is a false easting and false northing added to the actual coordinate. So it basically pushes everything, all the coordinates, to be positive, no numbers, and that makes the mathematics quite a bit easier. So that PRJ file, or that well-known text file that you are importing in with a shapefile, or you're using to create a coordinate system, that's what's in it. If you have a grid-based coordinate system, right, so let's say it's a state plane system, you've got to have the datum in there, right? And just having the projection information is not enough. You have to actually know what the datum is. In fact, if you import data into any GIS system and you don't have a PRJ file, for instance, you need to specify the datum and the projection of your spatial data. If you don't know both, you will have errors when you import the data. Okay, so what kind of coordinate reference system is right for your Geographics project? Well, really, it often depends on the type of vendor data that you want to import into it. IHS well locations are typically in the North American Datum of 1927. Obviously, we've been drilling wells in North America for a very, very long time, even before 1927. So a lot of the historical data, especially the spatial data for our well spots, are referenced to NAD 27, the North American Datum of 1927. NAD 83 is becoming increasingly common. Because we have good GIS software now, we can fairly easily convert our NAD 27 lat longs to NAD 83 lat longs using a shift file. The database coordinate system in Geographics typically, not always, doesn't have to be, but typically it's going to be a geographic coordinate system defined by a datum. Now, like I said, UTM and state plane are the most common coordinate systems that are used to define the map display system in Geographics. So, what is the first question you should ask yourself when you are presented with some spatial data, whether it be in a shapefile or a DEM file or something? The question you need to ask first are, what is the datum and what is the projection of that spatial data? If you know that and that's accurate, you can then import it into ArcMap or Geographics, and on import, that software will transform those coordinates into your project datum and projection. However, if you don't know that or you're just guessing, your spots are going to be off. Either your land grid's going to be off or your well spots are going to be off. Something's going to be off. So, if you take away sort of one thing from this presentation, it's that one, latitude and longitude depends on what datum you're in. And if you want to import data, spatial data, into any GIS tool, including Geographics, you need to know the datum and projection of that spatial data. Really important. Okay, and of course, satellite images we stream into Geographics, shape files, DEM, bathymetry data, all that kind of data that you're importing in, you need to know datum and projection. Now I'm just going to do a real quick demonstration here. Let me get out of here for a second and bring up Coordinate System Manager. A lot of you guys probably don't use Coordinate System Manager a lot. It's where all of the datums, map projections are stored and can be manipulated. You can also create a custom projection using the tool. We do use the Blue Marble Geodetic libraries for all of our coordinate transformations in Geographics. It's a very, very high quality geodetic library that supports practically every datum and projection and coordinate system worldwide. Now, sometimes you do need to create a custom coordinate system. So one easy way to do that is to go out here to a website called www.spatialreference.org. This is one of my favorite websites because it's so useful. If I type in here, for instance, NAD 83, and I search, and I can find out what the EPSG codes are for, well, pretty much every coordinate reference system imaginable. So I'm going to go out here and go to Colorado North, and that Colorado North feet US survey feet is represented by the EPSG code 2231, and I can export a PRJ file, an Esri WKT file, a file in JSON, a well-known text string, all of these different types of formats I can export. Probably for you guys, the PRJ file would be the most useful. So if you ever need a PRJ file in a specific coordinate system, this website is awesome for that. So actually, I went ahead and did that. And I'm going to import one of those PRJ files into Coordinate System Manager. Make sure it's there. And there's that 2231. And I'm going to open it up. Now you'll notice that, I'm going to create this coordinate system using Coordinate System Manager. And I'll need to do that because it's a US survey feed. And we don't support that directly out of the box, although we will. So I'll just do that, and I'll say OK. Now, it's going to always say failed because you didn't set the datum transformation method. You're going to have to do that. What is the datum transformation method? Well, that's the shift between, that's the transformation method that you're going to use to shift lat longs between one datum to another datum. Number of these methods are purely mathematical. Molodensky, Versa-Wolf, Molodensky, Badakis, on and on and on. But some of them aren't. Some of them use shift files. I'm going to go ahead and check NADCON 1983 and say that's the transform method that I want to use whenever I need to shift lat longs between one datum and another datum. NADCON, actually, the NADCON transformation, it's really a computer program developed by the U.S. Department of Defense. It has 15,000 reference points where the shift is defined in North America. And those reference, you interpolate, well, the program actually interpolates between those reference points to find the datum shift, the shift in lat long between one datum and another. I would always use the CONUS shift file. Okay, you'll notice I have a new reference system that I can use. When I create a Geographics project, I go projects, new project, and I'll just call my new project Geomatics. And go down here to North America, United States, state plane. And there it is. So I have a new coordinate system. It's defined. I've used my PRJ file to define it. And I can do that. But actually, right here, I'm just going to go ahead and make it a geographic coordinate system for NAD83. And then when I create my map coordinate system, I'll go ahead and select that Colorado North gridded system. Now, the only difference between it and Colorado North is it uses the U.S. survey feed as its distance, as its measure of distance. And I'll hit next, and then I'll finish up, and I'll create the project. Now my map display system is now U.S. survey Colorado North U.S. survey feed. Great. So just a little, you can do a lot of other stuff with Coordinate System Manager. There's tools here. You can go in and you can create a file with coordinates. You can transform those coordinates from any datum and projection to any other datum and projection, if that's what you want to do. So I know people don't go in here an awful lot. They don't muck around with it very much because they really don't have to. But it does have some nice features that allow you to, transform coordinates as you will. If you guys use ArcMap, that's another great tool for doing that also. Also, the Blue Marble calculator probably is the best tool for that. And the Blue Marble calculator is the tool that is sold by Blue Marble Geographics. And that's the libraries that we use, the geodetic libraries we use in Geographics. Okay, let's move on here. Okay, so one thing you want to sort of take from the whole presentation here is that what? Know the datum and projection of your spatial data before importing it into GeoGraphix. If you don't know both, you're going to run into problems. A lot of old data, you won't know both, right? It'll be like, oh yeah, this is in Colorado, some state plane coordinate system, but I don't know if it's in NAD 27 or NAD 83, if the datum's NAD 27 or NAD 83. If you ever run into that problem, import it, import the data. If it's just like a shapefile or something like that, import the data and then overlay it with a satellite image in the correct datum. And if things line up, you're good to go. If things don't line up, you know you chose the wrong datum. GeoGraphix, because it is a GIS system, reduces your risk of mistakes and maximizes your productivity. Because we can transform many spatial data types from a source coordinate reference system to the project coordinate reference system. Pretty much all the spatial data that you do import into GeoGraphix, we can transform on the fly if you do know the datum and projection of the source spatial data. Now, there are some great sources of information out there. Let me just go to a few. One that I already showed you was the www.spatialreference.org. If you are a GIS professional anywhere, not just in the petroleum industry, I highly encourage you to take a look at this site because it makes life a lot easier for you. But also, you can go to the Association of Petroleum Surveying and Geomatics website, www.apsg. It's a great organization for GIS professionals in the oil and gas industry. And of course, Esri has a lot of good materials out there related to geomatics.